What we're going to be working with is something called linear programming. Linear programming involves using a system of constraints along with an objective function in order to optimize, which means to maximize or minimize, a certain quantity. So let's start with a system of constraints. The system of constraints is the limiting or restricting factors. Now, in a real-world situation, that might be related to labor or the cost of the input, like natural resources or rent maybe for equipment. Then we have an objective function. An objective function is the quantity that you want to maximize or minimize. Again, in a real-world problem, that might be profit, if we want to maximize profit, or cost, if we'd like to minimize cost. An example of an objective function might be, well, out of context, might look like this, f of x and y. So it's going to be a function in terms of the variables x and y. So 5x plus 2y. In a real-world situation, it might be something like profit equals 5x plus 2y. Let's look at an example and work all the way through the steps. So here's my example. This is the system of constraints. A system of constraints is a system of inequalities. Whereas the objective function is an equation. So I'm going to be, as we go along through this problem, I'm going to be writing the steps for linear programming, kind of in that same pink color that the title is. So the first step in linear programming is going to be to graph the system of constraints. Oops, little spelling error. Graph the system of constraints. So we'll be graphing this system of inequalities based on the steps that we've been using for graphing a system of inequalities. So start with my coordinate plane. Usually when I'm working a linear programming problem, I will not use graph paper because I want the end result to be a nice looking graph that could be professionally presented. Now here I'm using notebook paper. Normally I would just use plain white paper. So let's graph these inequalities one at a time. So first I will graph y is greater than or equal to 2. Y is greater than or equal to 2 is going to be a horizontal line. So I need a ruler to make sure my lines are straight. So y is greater than or equal to 2 is a horizontal line through 2. And it's going to be a solid line. So I'll graph that. Remember that with a system of inequalities, you're only going to shade the overlapping region. So I'm just going to indicate that I will be shading up for y is greater than or equal to 2. And then I'll go on to my second inequality. X minus y is greater than or equal to negative 3. That's in standard form, so I'll graph that using the cover-up method. So I'll cover up the y. That gives me x equals negative 3. I'll use that. X equals negative 3. So that's going to be the x-intercept negative 3, 0. Then I'll cover up the x, and that gives me negative y equals negative 3. So that would mean that y would be positive 3. So negative 3, 0, negative 3, 0, and 0, 3. This is again a solid line. So I'll go ahead and connect those dots. And I need to test a point to shade, so let's test 0, 0. That gives me 0 minus 0 is greater than or equal to negative 3. 0 is greater than negative 3, so that's true. So I'll be shading towards my test point. So that'll be below that line. And then my third inequality, 2x plus y is less than or equal to 6. Again, I'll use the cover-up method. So I'll cover up the y. That gives me 2x equals 6. So the x-intercept would be 3, 0. And then I'll cover up the x. That gives me y equals 6. So 0, 6. So 3, 0. And 0, 6. 1, 2, 3, 4, 5. That would be up here. This is also a solid line. Connect those. And then test a point. So 0, 0 is going to work. 0, 0 gives me 0 plus 0 is less than or equal to 6, which is true. So that will be shaded towards my test point as well. So when you look at the inequalities all together, you can see that the shaded region is going to be below the purple, below the orange, but above the green. So it's going to be this kind of triangular region in here. Now that actually has a special name. The shaded part is called the feasible region. And that's going to be an important part of linear programming. So that's called the feasible region, and I want to caution you on something. The feasible region is not always the enclosed shape. It could have been this section over here or this section down here. So just know that the feasible region, which is the shaded section, is not always the shape that is closed in. It happens to be in this problem. So here's one kind of cool thing about linear programming, is that the part that we just shaded in, that feasible region, every point in that feasible region is a possible solution to our problem. So if we were in a real world situation, every point within this region would fit all of our restrictions. So let's go ahead and make a note of that. Every point in the feasible region is a legitimate and possible solution to the problem, to the linear programming problem. But remember that with our objective function, that's what we're trying to maximize or minimize. So what we could do is test every single point in here by substituting it into our profit or our objective function and see which one would give us the highest profit. That would take us forever because there's an unlimited number of points within that region. So it's kind of important to know that the best solution, which means the one that will give you the maximum or minimum depending on what you're looking for. Minimum value of the objective function that best solution will always, always, always occur at one of the vertices of that feasible region. So instead of testing 100,000 different points, we only have to test 1, 2, 3 of those points. So that's going to bring us to the second step in linear programming. So step 2 in linear programming is going to be to find the vertices of the feasible region. And the way that we're going to do that is that we are going to set up and solve a system of equations for each pair of intersecting lines. So if we kind of go back and forth between our graph and our work here, we'll see that we need a system of equations that would represent the intersection of the orange line and the purple line. So I'm going to be really organized as I go through and set up these systems. So maybe I'll label them equations 1 or inequalities 1, 2, and 3. So 1 will be my green line, 2 will be my purple line, and 3 will be my orange line. So this vertex right here is the intersection of lines 3 and 2. So what I'm going to do is I will create a system of equations using lines 2 and 3. And when I do that, I'm not going to write inequalities. I'm going to write those as equal signs. So I'll have x minus y equals negative 3 and 2x plus y equals 6. Then I want to solve this system of equations. Looking at what I've got here, I can tell that I could solve this very easily by elimination, just by adding those two equations together. That'll give me 3x. The y's will add to 0, and I'll get equals negative 3 plus 6, which is 3. Dividing both sides by 3, that gives me x equals 1. To get the y coordinate, remember I'm going to sub that in to one of my equations, so let's go ahead and put that into equation 3 there. So 2 times x, which is 1, plus y equals 6. That's 2 plus y equals 6, which gives me that y equals 4. So that vertex would be the ordered pair 1, 4. So we can go back to our graph and label this vertex right here 1, 4. Now what we're going to do when we come back is we will set up the system of equations to find this vertex and that vertex, and then we'll go on to the next steps for linear programming.